video, we'll just kind of quickly go through the review sheet that you have a answer key for already. I'll talk a little bit about what to expect on the test. But I strongly encourage you to try the review sheet on your own first before viewing the video. You don't get an opportunity to practice if you're just going to watch me do the review sheet for you. It just isn't going to work that way. You won't do well on the test. So please take the time first and then use this to go over any of the problems. Skip around to a problem that you need to review in a little more detail. So this first one is just a basic set of 1, 2, 3, we have 5 people. List all possible outcomes. Use the first initial so you don't have to write the names out. You can do this as systematically as possible so that you don't miss anything. Sorry about that. And the best way I would, and I made this easy, A, B, C, D, E. So you can kind of go through. So I would start A, B. Now, I can have A, B, C. I'm going to move this over so I have more room, actually. So I would start everything with an A, B first. C, D, E. All right? Now I've gone through all the A, Bs, I'm going to move to the A, Cs. So that's A, C. Now I don't need to work backwards. I already have A, C, B. A, C, B, and A, B, C are the same possible outcome. Because in this particular problem, we are just selecting from a group of 5. It doesn't matter the order that we are selecting them in. And that's an important piece to remember. If we were drawing names for president, vice president, and secretary, that would be a little different. A, B, C, and A, C, B would not be the same outcome. But we're just doing a sample space, which means we are just, the order doesn't matter. So A, B, C, and A, C, B is the same thing. So that leaves A, C, D, A, C, E. Now I've done A, Bs, I've done A, Cs, I need an A, D. And the only AD is ADE. It's the only thing that hasn't been included yet with the A's. Now I do the same thing with B. I start B, C, D. Well, I can also have B, C, E. All right, that's it for BC. How about skip the C and go to BD? We only have BDE. So we're done with the B's. Now I can move on to the C, C, D, E. And that should be it. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible outcomes from this group. And just to help you out here, another quick way to do this is a combination. This is something we talk about. It's on your formula sheet for when you're doing the binomial, which I think is in section 5.3. There is a formula on your formula sheet for the binomial coefficient. And the binomial coefficient looks like this. And what this means is if I have a group of 5, how many possible outcomes are there if I'm choosing 3 people? If you have a calculator, this is how it goes in your calculator. And if you're using a calculator, you will quickly just plug it into your calculator, find the combination key on your calculator. You're going to see you're going to get 10, which is exactly what we got. If you're using your formula sheet, it is a factorial, and it is n, which is 5 factorial over x, which is the amount we want, 3 factorial times n minus x. The difference between 5 and 3 is 2. So what are factorials? Just a reminder, it means 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. 5 minus 3 is 2. 2 factorial is 2 times 1. Well, here's the deal. When we're multiplying anything by 1, the 1's can cancel away because that's not going to change anything in multiplication. I have a 3 times a 2. I've got a 3 times a 2. 2 goes into 4, 1 time, 2 left over, 5 times 2 equals 10. So either way, we get 10. You don't need to do that. You can just list them, but understanding how many outcomes, when you have a larger group, how many outcomes of a certain size you can possibly get using combination is a nice, easy way to do that. But again, for the actual problem, you only had to list them. Assuming Charlie and Dave are the only males, what is the probability that at least one male will be selected? So what are you doing? All we're doing is figuring out the probability of at least one male. So you're counting. And basically you're counting how many in my group of 10 have at least a C or a D in it. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. You can see the only one that doesn't is here. So that's why it is 9 out of 10, which is 0.90. What is the probability that exactly 2 females will be selected? So here you have to go through and check off all the ones that have exactly 2 females. Well, remember your females are A, B, and E, and you want 2 of them. Well, there's 2 there. There's 2 there. There's 2 there. 2 there. 2 there. 2, 3, 4, 5, and 2 on that one should be 6. Yep, I think that's it. So probability of exactly 2 females is 6 out of 10, or 0.60. What is the probability that no females will be selected? Well, considering we only have 2 males and we're doing groups of 3, it can't happen. And a probability that can't happen, of course, is a 0. All right, number 2. So for this one, please make sure you have your sheet, your table in front of you. You're doing a normal distribution. So chances are you're going to have to use that Z table. And X is normally distributed. So what does that tell you when it says X is normally distributed? That means I can use a normal distribution to help me solve this. The mean is 60, mu is 60, so mu goes in the middle. Remember, this is the unstandardized version. And standard deviation is a 4.0. Now, I want the probability that a number selected is less than 53. All right, so if 60 there, where's 53 is going to be out here somewhere. And I want the probability that it's smaller. So that area under your normal curve is what gives you the probability. So you want this area from a 53. But as you know, we cannot just simply look up 53 on our table. So I have to standardize, which means I got to redraw my normal curve with a 0 in the middle. And my 53 is no longer going to be a 53. Well, we need to figure out what it's going to be. It's going to be a z-score, where we take our x value minus the mean, divide it by that standard deviation. So go ahead and calculate that. I get negative 1.75. So far we're in good shape. 53 is less than 60, so we got a negative z-score. That makes sense. Now we want the area to the left. That makes it certainly easier to look up our formula sheet. We go to negative 1.65. Oh, I'm sorry, negative 1.75. So that's 0, 1, 2, 3, 4, 5. And we get, let me double check. Yep, that's the 5.0401. So, what is the probability that x is less than 53? It is only about a 4% chance. When they ask for probability, keep it as a decimal. Only if you were specifically asked for percent do you change it to a percent. Okay. Now for this next one. Now I want the probability when my mean is 22. Remember, I'm drawing it unstandardized first. I want to be between 19.7, it's over here somewhere, and 25.3. I want this area in the middle. Well, to get that, remember, you have to find two areas and subtract them from each other, but you can't find those areas until you standardize everything. So I want you to go ahead, stop the video if you haven't done this already, because again, if you're just watching me do this, you're not going to learn how to do it. And get the two standardized numbers for 19.7 and 25.3. 19.7 minus the mean divided by the standard deviation, which is 2.4. And of course the other one is 25.3 minus the mean divided by 2.4. So go ahead and calculate those two standard, not your standard deviation, but your standardized scores. So that 19.7, it looks like it becomes negative, I round it, negative 0.96. And that 25.3, of course, is going to be positive. If I minus 22 and divide by 2.4, it looks like I get 1.38. Okay, so what you need to do now is go ahead and find those areas. So again, 1.38, the area all the way to the left is 0.9162. You got to get that from your sheet. I'm not going to keep going back to the formula sheet. You should have that in front of you and should be able to find it. And then the area of negative 0.96 to the left is going to be a much smaller area. Of course, it's 0.1685. To get what's in the middle, you're going to subtract. And if you subtract, you should get the 0.7477. Okay? Moving on to the next problem. Suppose a card is selected at random from an ordinary deck of 52 playing cards. You do need to know what's in a normal deck of playing cards. If you go to your textbook, it is in Chapter 4. It gives a nice picture of an ordinary deck of cards. I will always write on the test that we are talking about 4 suits, you know, ace to king, and the colors of those suits. So I will describe it for you in case you've never dealt with a deck of cards before. So we have 52 playing cards. A equals the event a queen is selected, and B the event a diamond is selected. So, you know, if I was finding, and again, this is just a little extra, if I was finding A on its own, well, that would be easy. There's 4 queens out of 52. If I was finding B on its own, diamond, well, there's diamond is one of the suits. It's a quarter of the deck, so it's 13 out of 52, which is 1/4. Okay, that's the probabilities on their own. But this bar right here is a conditional probability. So I'm going to determine the probability that a diamond is selected given, and that's the word you say, given I know a queen has been selected. So here's the deal. You no longer have a full 52 playing deck of cards. You have a condition. Your condition is now that you know the cards are a queen. So how many queens are in the deck? There's now only 4 queens in a deck of cards. So you no longer have 52 cards, you're down to 4. And what's of those 4 cards, how many of them are diamonds? 1. Okay, notice the probability is the same with the condition. as it is without the condition. All right, sometimes that happens and sometimes it does not happen. That is not always the case. And in this case, because their probabilities with the condition is the same without it, we would say that event B is actually independent of event A. If those probabilities were not the same, then they would be, event B would be dependent of event A. Okay? But in this case, it is 1/4, which of course we write probabilities as decimals, 0.25. All right, the age distribution of students to community college is given below. Here we go. All right. Every possible age is given. You were given the raw data. You were not given the probability. So this is where you got to be careful. Sometimes you're given raw data. Sometimes you're given probability. Sometimes using formulas makes sense, and sometimes using kind of what I call common sense makes sense. So let's take a look. Find the conditional probability that a student is at most 35 given that he or she is at least 26. So we're going to use kind of common sense for a minute. We're going to ignore the formulas and just go with what does a conditional probability mean? Given that they are at least 26 means I am now going to limit to this group of people. No longer have a full 1091. I am going to limit myself to the 208 plus the 50 plus the 21 to these, 208 plus 50 plus 21 to these 279 people. I am only looking at these 279. That's what a condition does. It gets rid of the whole sample space and lets me focus on just a small portion of it. Now, I want the probability the student is at most 35. All right, go within your new little sample space, and at most 35 would be these. At most means you could be 35 or younger. So now the probability is going to be 208 plus 50 over that new total of 279. And it looks like if I round it, I get 0.925. So that's one way to do a conditional probability, just kind of thinking through the problem. Okay. And just as a note, let's look at the formula sheet for one quick second, because sorry, to go back, way back to chapter 4, because we do have formulas for our conditional probability. And here is a formula for conditional, which works really well if you are given the actual probabilities and not the raw data. If you were given the probabilities, then you would use the probabilities that you were given and plug it into this formula to get your condition. All right, let's move on. If 2 fair dice are rolled, find the probability of a sum of 6, given that it's a double. There it is. Where's your given? How many doubles can you get? You get double 1s, double 2s, double 3s, double 4s, double 5s, double 6s. So we're out of 6. How many of those doubles add up to 6? Well, only one of them, 3, 3. So it's simply 1 out of 6, which is rounded to 0.167. All right. Again, that given really limits. There are 6 doubles, and only one of them has a sum of 6. 2 cards are drawn without replacement from a deck. Find the probability that the second card is red, given that the first card was a heart. So this one's a little bit trickier because we are drawing 2 cards, all right? So you have the first card and the second card. All right, we know that the first card was a heart. And we want to know now what would be the probability of that without replacing the first card, without replacement, what would be the probability that the second card is red? Well, let's think about this. Because of this condition, we no longer have a 52 deck of cards. We're actually down to 51 cards because we took that first card out and we're leaving it out. So now we have 51 cards. Okay? All right. Normally, half of the deck is red. So that means normally we have 26 red cards. But that first card was a heart, and we know hearts are red. So we no longer have 26 red left in there. We have 25. So we're doing 25 out of 51, which 25 divided by 51, I believe, does work out nicely, 2.490. Number 8, the following contingency table. All right. So we've got a big contingency table going on. Suppose one of these people is selected at random. Compute the probability that the person selected was a college professor, given that their age of retirement was between 56 and 60. So again, between 56 and 60, we are now limiting everything to just this column, ignoring everything else. We want the probability that they are a college professor. Well, and that's 46. So what I want is the 46 out of 165. Which should come out to about 0.279. Okay? All right, number 9. Yeah, 0.279 is correct. Okay, for this one, we're just using notation. You don't really need to do anything but set it up correctly. Let Y denote the number of living grandparents of the student. Use a random variable notation to represent the event that the student has at least 2. At least 2. So, using notation, it's probability that Y, all right, at least means it could be 2 or could be greater than. That is your answer. You know, sometimes it's between 1 and 2, and you got to use a larger inequality. But that's all you had to do for that problem. All right, evaluate the expression. Again, you can actually use your calculator. That is a combination. It looks like that in your calculator. Or use factorial, which is 11 factorial over 3 factorial. And then what is 11 minus 3? That would be 8 factorial. I'm just going to use factorials real quick. And this is how I do it. Well, that's 11 times 12 times, sorry, I don't even know why I wrote that. Let me do that again, times 10 times 9. Now, I'm just going to write, instead of writing 8, 7, 6, 5, 4, 3, 2, 1, I'm going to leave it like that because they will cancel away. And 3 is 3 times 2 times 1. All right, well, 3 goes in there once, there 3 times, once, and 5. So I am looking at 11 times 5 times 3, 165. Okay, that's how I use the factorial. You can also plug this into your calculator for a combination, and you will also get 165. All right, determine the binomial probability formula given the number of trials and the success probability for the Bernoulli trials. Let X denote the total number of successes. All right, so you're given all the information, and you are going to use, we're going to find the binomial probability of X equaling 2. So I'm going to go get that formula for you. This is just on your formula sheet. This is a binomial. Okay, so it's, here it is. The binomial probability formula is this one right here. It's really not that difficult to use. Let me go ahead and write it out for you. All right, so the probability of X equaling 2 is, so it starts with that N choose 2. So there's 5, and I'm choosing 2. Then notice, so I did that part, N is 5. It's good to kind of figure out what each piece is. Okay, now I need the probability of a success, and I take that to the second because I want 2 successes. So the probability of a success is 0.6. So I'm going to have 2 successes because that's my X value. And then, oh, I need the probability of failure. Well, the probability of success is 0.6, failure is 0.4, times the difference between N and 2. So I have 0.4, and then of course N minus X, 5 minus 2 is 3. So that's my formula. Remember, N is 5, P is 0.6, X equals 2, and then 1 minus P is 0.4, and of course N minus X equals 5 minus 2 is 3. All right, you can get this into your calculator. Again, you can, like we did above, you can use the factorial formula for 5 choose 2, or you can use the 5C2 in your calculator. Either way, you are going to get that number to be 10. So this equals 10 times 0.6 squared times 0.4 cubed. I'm just going to go ahead and plug those numbers into my calculator. Go ahead and it looks like I'm going to get 0.2304 for those. Okay. So for this problem, in a city, 25% of the population is under 25 years of age. 3 people are selected at random from the city. Find the probability distribution, the number among the 3 that are under age 25. So there's a couple things. You do not need to draw a tree diagram for all the possibilities. If you did, it would be long. You can do it. It kind of is like, but I am not going to make you draw a tree diagram on the test. And you do not need to draw a tree diagram to solve this problem. In fact, I would say skip that entirely. I want you to learn how to use the formula. So here's how we are. 3 people are selected at random. So that's our N. N is 3. Probability of success. What is success in this problem? Success in this problem is getting someone under the age of 25. So the probability of that happening is 0.25. So what's my probability of failure? 0.75. All right. Now notice they don't give you an X because they want you to do the entire distribution. When you do an entire distribution, come down here. We check when X equals 0. Because out of 3 people, there's a chance you could have 0. There's a chance you could have 1. There's a chance you could have 2. There's a chance you can have 3. That is your entire distribution. For each of those X values, you are going to use the formula. 3, choose 0. Probability of success, 0.25, x is 0, 0.75, 3 minus 0 is 3. You do it for each of them. You got to do it for each. This one's, whoops, sorry. 3 choose 1. Now I am looking at one success, and if I have one of them under 25, that means the other two are, that's n minus x, 3 minus 1, are over 25. Now I do it for x equaling 2. 3 choose 2. I have 2 people. What's the chance of 2 people under 25? Which leaves me with 1 over 25. And then, of course, the last one is 3 choose all 3. I have all 3. And then I have none of them under. So I did that to show you that these formulas are pretty straightforward. You can go ahead and use your formula. Here's what's nice. There's only one way to get none of them, so that ends up being 1. Now, anything to the 0 power is 1. So really, this first one is 0.75 cubed. Same here. That's 1. That's 1. The last one, because it's all of them being under 25, is 0.25 cubed. And then you can go through and do 3 choose 1. And you can go through and work all these out. Okay, it ends up being 3 times 0.25 to the first, 0.75 squared. And 3 choose 2 is 3 again. This time it's 25 squared. All right, so you just got to work all those out. And if you do that correctly in your calculator, you do get and of course you get 0.4219. Total coincidence here that that is the same. You should add them up, make sure they come out to approximately 1. What is the probability that at least one person will be under 25? At least one person will be under 25. So that means it's the probability of one person plus the probability of 2 plus the probability of all 3. Because at least one means you could have any of them. So you would add up 0.4219 plus 0.041406 plus 0.0156. And when you add those up, I believe you get 0.5781. You could have also went to 1 and just subtracted out that first 0.4281. Okay, here's another binomial. You're given a percent of all students where that's your P. Find the mean for the random variable X, the number of students who work full-time in samples of size 16. All right, so you want a mean here. The mean when we're talking about binomials is the expected. So 22% of all students work full-time. So that means if we had a sample size of 16, how much would you expect to be working full-time? You can certainly go to your formula. The mean of a binomial is simply mu equals NP. That's it. And there's your standard deviation of a binomial. That's of a binomial. So we have, it's just 16 times 0.22, which makes sense. It would be 22% of the 16. So it's just about 3.52, and yes, you do leave it as a decimal. And then the standard deviation, again, we are dealing with a binomial, so your standard deviation is NP times 1 minus P. So it's the square root of N times failures, which would be 7, 8. And that will get you your 1.66. The area under the density curve that lies to the right of 12 is 0.405. What percent of all possible observations are at most 12? So again, start drawing it out. The area under the density curve that lies to the right of 12 is 0.405. Okay, so that means 12 is over here somewhere. If this, keeping in mind the whole thing, half is 5, so it's less than half, is 0.405. What percent of all possible observations of the variable are at most 12? Well, all they want is everything over here, and this is just, you understand that the entire curve is a 1, so you subtract 1 from 405, you get 0.595. They asked for a percent, so 59.5%. All right, for number 16, again, draw. I saw the word normal distribution, I'm going to draw it. So it's 35 is the mean. And we want to know the percentage of time that his commute time is less than 44. Well, if that's the mean, then 44 is going to be over here somewhere. I want less than is equal to the area under the standard normal curve that lies to the, obviously it's left of, well, I can't put 44, I need to standardize. It's 44 minus 35 divided by the standard deviation of 5. And I believe that comes out to 1.8. Okay? Use a table of areas to find the specified area under the standard normal curve. Again, draw. 1.13, it's standardized, so that's over here. Lies to the left. I just want that area to the left of 1.13. Go to your table, 0.8708. All right, so you can do this by getting the area to the all the way out to here for that one and out to there for that one. So the area to the left of 1.17, again, go to your normal curve, looks to be about 0.8790. And the area to the left of negative 1.17 is 1210. So you simply subtract them to get that 0.7580. Okay. Find the z-score for which the area under the standard normal curve to the left is 0.96. Draw it. All right, you want the area to its left. Well, that would be a lot, so it's got to be out here somewhere. 0.96 is covering almost the whole curve, because the whole curve is. So I go to my normal. Sorry, let me scroll down. Go to my normal distribution, 0.96. That is an area. Okay, and this is where you got to be careful. You've got to read the problems really carefully and know, okay, the 0.96 they're giving me is an area. That means I got to look in here for it. I got to look in here somewhere for it. So 0.960. Well, this one's really close, 0.9599. fact, that's probably as close as you're going to get. That's 9608. 9599 is closer than 9608. So I'm going to use 1.701234.5. 1.75. Okay. The volume of soda in a quart soda bottles are normally distributed with the mean of 32.3 and a standard deviation of 1.2. What is the probability that the volume of soda in a randomly selected bottle will be less than 32? You can draw it. All right, has a mean of 32.3, standard deviation of 1.2. They want to know probability is less than 32 ounces. That's actually here. And it's less. So again, you got to standardize it. I want 32 minus 32.3 over my standard deviation of 1.2. So that's what? Negative 0.3. And it's negative 0.25. Okay, that is this number standardized. I still need the area. You got to go to your chart for that. Go ahead, area to the left of negative 0.25 is going to be really close to 0.5, but not quite. It's 0.4013. Okay, they're not asking for a percent, so keep it as a probability. All right, now I'm going to do number 21. The ratings are normally distributed with a mean of 200 and a standard deviation of 50. If an applicant is randomly selected, find the probability of a rating that is between 200 and 275. Okay, so here it is unstandardized. The mean is 200. That's already given. And that's the mean. And then we've got 275 would be out here somewhere. And they want what is directly in between. Well, we got to standardize it. The 200 becomes 0. And 275, not 257, is, let's see, 200 minus 275 divided by the standard deviation of 50. Looks like you get 1.5. Again, I'm rushing. I apologize for that. It was 2. I know you're sitting there thinking, but doesn't that go first? Yes, it does. And it's 1.5. So all we did was standardize 200. 200's easy because it's 200 minus 200. Well, that's just 0. Any mean standardizes to 0. So we want to know the area in between them. And whenever you're given 2, you need the one all the way this way compared to that one. Well, this is 0.5. You can look up 0. It's just 0.5. And of course, 1.5 comes out to 0.9332, I believe. So it's 0.9332 minus 0.5. Okay, so again, this review sheet does not necessarily cover everything. It just gives you a little bit of practice on certain things. I do want to kind of go over one other type of problem with you, and that has to do with a discrete random variable, and this was not on the review, but this is section 5.1 and 5.2 that had gotten some questions out. It's just a discrete random variable. And this was 5.1 to 5.2. So if we are given the information with a discrete random variable, you are given the probabilities. Okay, so you will already be given. So let's suppose that in any given month, a particular fire department in a rather small city has a, this is the probability, the probability of having 0 fire calls is 0.48, the probability of having 1 is 0.36, the probability of having 2 is 0.14, and the probability of 3 is 0.02. Okay, so this is a probability distribution you're given. This is very different from the binomial. In the binomial, you actually have to calculate what each of these probabilities are. But with a simple random, or the discrete random variable, you're given those probabilities. So you've got this idea. You've got, all right, and this is again, the calls that go out for a small little town fire department, they never get more than 3 a month. And there's a 48% chance they get none, a 36% chance they get 1 call, a 14% chance they get 2, and a 2% chance they actually get 3 calls in 1 month. So here's what I want to be able to do with this. I want to be able to find the mean and standard deviation. Okay, this is a little bit more complicated. You go to your formulas for your discrete random variable. Again, it's all the way at the front. I need to get to chapter 5. Okay, and here are the 2 formulas you're using. There's the mean, and there's the standard deviation. And I just want to go through and make sure you know how to use these formulas properly. So for the mean, you are taking the summation of each variable times the probability of it happening. So what does that mean for the mean? Let's do that first. I want the probability, I want to multiply each variable times the probability that it happens. That means 0 times 0.48. It means 1 times 0.36. It means 2 times 0.14. And it means 3 times 0.02. Now I'm going to sum those up, and that's going to give me 0.7. So the mean, I'm going to erase this from here, sorry. So the mean equals 0.7. And remember, the formula was summation of x times the probability of getting that x. So that means you have to multiply each and then sum them together. All right, we need the mean for the standard deviation. The standard deviation is a bit more complicated. Your standard deviation, I like to use this first one. You can use either one. I like to use the first one. So what do I have to do? I have to take each x, subtract it from the mean, square it, then multiply it by the probability. All right? So I'm going to do each x minus that mean, square it, and multiply it by the probability. All right, what's my first x? My first x is 0. So that's 0 minus 0.7 squared. And what was the probability of 0 happening? Times 0.48. The second one, that actually comes to 0.2352. Now for the second one, my x is 1. 1 minus that mean squared times, what's the probability of that happening? 0.36. Okay, multiply that out. Oh, sorry. And then the next one is 2 minus 0.7 squared. If you organize your table good with your formula in it, these become much easier to actually work out. And the probability of getting a 2 is 0.14. And work that one out, I get 0.2366. And the last one is, what's 3 minus that mean squared? Probability of that happening is 0.02, and that's 0.1058. Okay, so you sum that, because again, the formula for standard deviation is the summation of the square root. If you're not sure, come back here. It's a summation, it's square root, sorry, of the summation. So it is the square root of the summation of x minus mu squared times the probability of getting that x. So when I sum them, I get 0.61. Don't forget, though, the standard deviation is actually the square root of that sum, and that gives me 0.781. So you are going to have to know how to get a mean and standard deviation from an original set of discrete random variable probability distribution. I will give you what's in red, and you will use the two formulas for discrete random variable, mean, and standard deviation to get the rest. Good luck, and hopefully going through this review sheet will help you for the test, which is coming up.